Welcome to my channel. In this video, we are going to discuss ridge regression. This is an important topic in machine learning, data science, and adaptation processing. In particular, we'll try to understand what is ridge regression and its use. Now we'll start from regression, basic concept. Here we have considered 14 data points where x is independent variable and y is dependent variable. Now we'll try to fit a curve through these points, and primary objective is to predict the value y for one value of x which is not mentioned in this data set. Suppose at the point x equals to 2.5, at this point you will see the value is not mentioned. So we wish to predict the value of y where x is 2.5. Because we are having only finite number of data, all points of x are not given. So we need to find one curve that will fit through these lines so that we can predict the values of y for any value of x. So this is the objective in regression. Now we can fit one straight line. We can try to fit one straight line through these points. In that case, we'll consider y hat is the predicted one equals to w0 plus w1x. This is the equation of a straight line. So we can find these two coefficients w0 and w1 such that this straight line will fit in an optimal sense. That means it will create minimum error. So in the best way, we can fit this straight line. But again, you see these data points looks like it is having some non-linearity. So one straight line cannot pass through all the points. Meaning is that you cannot make error 0 through these lines only. Okay, so it's better to move to the nonlinear regression model. Okay, so we can go for polynomial regression. And now if we go for order number 3, that means then in that case y hat could be considered as w0 plus w1x plus w2x squared plus w3x cubed, this polynomial. So here we'll try to find out this w0, w1, w2 and w3, these coefficients, so that this curve will fit in optimal sense. So it may look like this, and here you'll see it can capture this nonlinearity a little bit, though it cannot pass through all the points. Means still some error is there. So we can again try to minimize the error. We can try to find one curve that will pass through all the points. Then only error will become 0 perfectly. So if we increase the order of this polynomial, we can attain that kind of situation. Okay. So you see, if we consider order number 10, in that case, y hat is basically summation of wj xj s to the power j, where j equals to 0 to 10. Okay, so if you tune this coefficients w0 to w10 in optimal sense, then you may get this kind of curve. And you see here, this curve is passing through all the points. It implies that the error is almost 0, almost all through the points, right? Now we'll try to compare these three situations. So clearly it says that this linear regression is not good enough because it cannot capture this nonlinearity in data set. And this polynomial with order number 3, it's good. Okay, it can capture this nonlinearity. but still some error is there. And with the order 10 or higher, you can see that the polynomial will pass through almost all the points, and obviously it is giving very less amount of error. Okay, so which one is better? Now we'll consider one term, bias. This bias is related to the total error in the regression model for training data sets. So in this case, we are having these 14 data points. These are all for training we have considered. We want to tune our coefficients, model coefficients, with the help of these 14 data points. Okay, so after fitting this curve, whatever error you will get at the end, okay, basically root mean square, we can call these things, that value is called bias. So easily we can understand that this linear regression will give large error, little bit, okay, more error is there. And here you can understand that errors is less because it is all the points are closer to this line. And here the error is minimal, almost zero. So I can say that for linear regression, bias is high. For this polynomial regression with order 3, the bias is medium, and for third one, the bias is low. Right? Now, we want to understand how it is behaving with respect to testing data. Suppose if I give one test data that is not yet mentioned in this training data, it is different from training data. Generally, the total data points are divided in two groups. So 50% we can consider for training, and rest 50% we can keep for testing. We want to check how model is trained. Okay, so for testing data, it should give less error again. Okay, so here you see that this one point I have considered here. When x equal to 2.5, that time y is 35. So this is the point. These are the 3 points. Now look at this first model, the linear regression. There you see this much error. Okay, and here this point is very close to this curve, and here you see this is the error, huge error. So now you see, so this is the predicted error, predicted y, and this is the actual y target. So this much gap is there. This is the error, and here the error is very low, and here error is large because this curve is having somewhere undershoot and somewhere overshoot, and this undershoot overshoot may be too large. So at this instant, whenever the point is shifted little bit, that time the predicted value could be very large or very small, so leading to very high difference between target and estimated one. Okay, so that difference, this, now here we will consider one term, variance. So variance is related to total square, or you can consider also average value of the square of errors in the model for testing data. Okay, so that variance we are talking about for only testing data. So we can understand that the linear regression will give medium error, and this one will produce low error, means low variance, and this one can give you very high, rather huge variance. Okay, now if we compare these 3 model, though the last one, the polynomial regression with the order 10, it is giving very low bias for training data, but it is giving very high variance for testing data, and this is dangerous because we are more interested for testing data. It should produce very low amount of variance for testing data. So you see, we don't know what should be the optimal order for this polynomial, which will give you good bias, means medium bias, and low variance. That is not known. So generally we will try to move toward the higher order polynomial. Okay, so but you see, whenever we will go for higher order polynomial, it may happen that variance will become very large. Okay, so in these three situations, we can call the first one, we can call it underfitting, because this straight line is no longer useful to fit all the data points, because these data points are having some non-linearity. Okay, so that's how it is called underfitting. And second one, we can call it balanced. It's a good one. And last one, with the order number 10, we can call it overfitting. It is too good. So this fitting is too good. This bias is low. It is good for training data, but it is leading to high variance for testing data. That is dangerous. Okay. So what I am saying that generally to capture this nonlinearity, we have to move towards polynomial regression, and we don't know the optimal order size. Thus, we'll try to go toward the higher side of this order, but in that case, it may give you very high variance. Okay, so that is the problem. So how to overcome this problem, this overfitting problem? So before that, we'll try to understand this polynomial regression a little bit in detail. So this y hat, we can represent this in this polynomial form: w0 plus w1x plus w2x squared plus w3x cubed up to wm x to the power m. So this summation form. Okay, sum of wj x to the power j, where j equal to 0 to m, and here m is your order of the polynomial. And here we will consider this x1, y1, one data, x2, y2, second data, like x3, y3, and up to xn, yn, there are n training data points. Okay, with the help of these n training data points, we'll try to tune these coefficients w0, w1, w2 up to wm, so that it will fit the curve. This polynomial will fit through the points. Okay, it will give very less amount of error. Now, so as those are the data points, what we can consider? So if I consider x1, y1, okay. So if I replace x by x1, then it is first one is w0, second one is w1 x1, then w2 x1 square, then w3 x1 cube, and last one is wm x1 to the power m. So this one will give you one expected value. I can say y1 hat. Okay, that may not be same as actual y1. So this y1 minus y1 hat is actually difference. That difference is called one error. We'll consider as epsilon 1. Thus, y1, we can write this y1 hat, this summation is y1 hat plus error. So we are assuming that it can have certain errors. Similarly, second data, we can have one error epsilon 2. For final data, we can have error epsilon n. So we'll consider all the data simultaneously. Then we want to consider the total errors, and we want to minimize this total error. Okay. Now we'll try to rewrite this one in matrix form. So this one, this y1, y2 up to yn, we can collect in a vector form. Similarly, this one epsilon 1, epsilon 2, epsilon n in a column form. So this will give you one column vector, this will give you another column vector, and this part we can rewrite. You see, everywhere the coefficients are constant, w0, w1, w2, here all w0, w1, w2 like that everywhere. Okay, only these things x1, x1 squared like this. Okay, so here all the polynomials with respect to x1, second row all the polynomial with respect to x2 only, like that. So again, so this is a beautiful symmetry that we can exploit. So you see, we can rewrite that one as this is one column vector y1 to yn, and this one is epsilon 1 to epsilon n, and this one, you see, this matrix, the first one is all 1, and second column is x1, x2 up to xn, and third column is square of those things, x1 square, x2 square, xn square. Likewise, next one is x1q, x2q up to xnq. In that way, the last column would be x1 to the power m, x2 to the power m, xn to the power m. So this matrix, when it is multiplied with this coefficient vector w0, w1, wm, you see the first one will give you 1 into w0, x1 into w1, x1 square in w2, like that. So those addition plus epsilon 1 will give you the first equation y1. I hope this formulation is clear to you. Okay. Now we'll consider this vector as a y vector. So we'll put underscore to indicate it is a vector, and capital letter we'll use to indicate it is a matrix. So capital letter with underscore, it is a matrix. So this is a matrix, and you see the dimension. So we are having n rows, this one row like that, n rows will be there, and we are having capital M columns. So it is n cross capital M. This is the dimension for this X matrix. Okay, and this vector is n dimensional vector, and this W vector is m dimensional coefficient vector. These coefficients m unknowns. So we are interested to find out these coefficients, and these are the errors, so n dimensional errors. Okay, so we can write in this compact form y equals to capital X W plus epsilon. So we can extract this epsilon vector as y minus capital X W. Now we can consider one cost function, one value considering all the errors. So obviously that cost function should be one scalar function. So from this vector we need to get one scalar value. So we can consider here the simple one, norm2 square. Okay, so j of w will be norm2 square of this error vector. Okay, so it is basically y minus xw, that norm2 square, and you know that norm2 square is basically the summation of square of each terms. Okay, means epsilon 1 square plus epsilon 2 square plus epsilon 3 square, like that up to epsilon n square. If you add all those things, you will get norm2 square. So this norm2 square we can consider as a cost function. We wish to minimize this cost, and then we'll try to find out this w vector. So we wish to estimate w, we'll call it w cap or hat. So this thing will be argument minimum of j of w for w vector. That w vector we are looking for, which will give you minimum cost. Okay, minimum loss or minimum cost. So okay, so here this one, this norm2 square should be minimized. So this problem, this minimization problem, it is having one solution, and that is called least squared solution. So you see the least square, so the square value will attain the least value. That solution easily we can obtain, and its form is like this: capital X transpose X and whole inverse, then capital X transpose Y. Okay, and this is the important formulation. Okay, this is the one result. So we need to understand this thing, because we are going to discuss Ridge regression, so we have to understand this part well. So first we will try to prove this thing quickly. Okay, so and its proof is very easy. You see, so we'll start from this cost function. So this is your L2 square, L2 norm square, right? So that we want to minimize. So this L2 norm square we can rewrite as its transpose times this one. So norm of, you see, anything norm of a vector, that square, we can write a transpose times a, where we are considering that a is a column vector. Okay, a is a column vector, right? So whenever a is a column vector, its norm is simply you can write a transpose a, because you see this is suppose a 0 square, a 1 square, 2 square like that up to n squared. So it's n dimensional. So here also this dot product will give you same form, right? Okay, now we can expand this product. Then you will get these 4 terms, very simple one. So first term will be y transpose and this y. Second one, its transpose. So x w, its whole transpose will give you w transpose x transpose, because we can consider a b whole transpose is b transpose a transpose. So this term is its whole transpose times y. Then next one is y transpose and this one xw, y transpose and xw. And last one is this transpose times xw, and it transpose is w transpose x transpose, and this is xw, and this sign is minus, it is plus. Okay, so you see this is having 4 terms and we wish to minimize these things. So standard way is that we need to take derivative of this cost function with respect to each w values. So basically we wish to find out the gradient of this vector. Okay, so gradient of this vector is defined at del j upon del w, the partial derivative with respect to w vector. So we're taking derivative with respect to vector, be careful. So first term is independent of w, so that it is 0, and second term is double transpose and something. So if I take derivative with respect to w, then we'll get only this one, this part, x transpose y. Okay, and next one is y transpose x. This is one constant and only w is multiplied. Then if I take derivative with respect to partial derivative with respect to w, then its transpose will get. Okay, and last one, this one will get, actually w square is coming easier, so 2 times of w. So in short it will be 2 into x transpose x into w, but it is not so simple. Okay, so we can prove that one, but here I want to skip these things. But if you take derivative of this one, easily you will get this one. Okay, so basically this one we can consider, suppose j1 is a transpose w in this form, the dot product, then partial derivative of this j1, you see del j1 del w naught. If I take derivative, then only I'll get a0. Second one, del j del w1, I'll get only a1. Similarly, last one, I'll get a n. So this will give you one vector that is nothing but your column vector E. Okay, so thus I have said that whenever I'll consider these forms, okay, so you see if j, this partial derivative del a transpose w del w, or del w of w transpose a, it will give you a, because a transpose w transpose a, it is same value. Okay, so you see here, so when it is a transpose w, then if I take derivative with respect to w, I'll get only a, the transpose of this one, and for this one w transpose a, I'll get only a, same thing, no transpose. Thus first one no transpose, and second one these things, you see in this form I have got one transpose. Okay, now del j del w, now we can simplify these things. So if I consider these things, you will get x transpose and y transpose transpose, it will give you again y. So again x transpose y, and this is also x transpose y. So if I combine these two, I'll get minus 2 times x transpose y, and this is plus 2 times x transpose x w. Okay, so for this optimal solutions, if I consider w hat, so at that value it should give a null vector, so that we can use it. So when we replace w as w hat, it should produce null vector. So now we can solve these equations. So 2 we can remove, and we can consider this x transpose x w vector, w hat vector is equals to simply x transpose y. Okay, now if I multiply both sides, it's inverse. X transpose x, it's inverse, left side. So left side you will get w hat, and this side it is x transpose x inverse, and this is x transpose y. So you see this result. So this is proved. So it's not too difficult to understand, but we'll be using this expression to understand this ridge regression. Now we are coming to the ridge regression. So before that, again, we'll come back to that three situation. One linear regression and last two polynomial regression with order 3 and 10. And we have seen that linear regression is not sufficient to capture all the nonlinearities. Thus, it is underfitting problem. And this moderate order, this bias is medium and variance is also low. So it's good for us. But here difficulty is to understand, to find this perfect value for this order. Okay. So if we go for very high value for this order, then there's a chance that bias will be very low, means this curve will fit all the data point perfectly, but variance for this testing data will be very large, a huge one. That is called as overfitting. So we used to overcome this overfitting because we don't know what could be the ideal value for this order. Okay, so generally we will go for higher order, but still we want to get low variance. That is the objective. Okay, so if I consider, so first we'll discard linear regression because it is of no use right now. We are considering only these two, and for these two the solution is these things. W hat is x transpose x whole inverse x transpose y. Okay, and here you see the dimension for this one is m cross n. Okay, and this is your m cross n, this is n cross 1, and this is your m cross 1, right? Now my claim is that if you increase this order of this polynomial, means m is increasing, then it can fit all data point well, imply that bias will reduce. Okay, whenever m is increasing, bias is reducing. Okay, that is obvious. And next, it will happen. So whenever you will increase this m value, there's a huge chance, not only chance, it will surely, this w hat will explode. Meaning is that the weight value coefficients is becoming very, very large, huge one. And this is the fact, because as this w value is very large, thus it is giving huge variance. Okay, so this is one important concept. Whenever you will try to increase this order of this polynomial, then w will explode, means w value is increasing rapidly, and this in turn will create huge variance. Okay, so this is my claim. Now we need to understand this thing, why w value will increase rapidly. Okay, whenever we will try to increase this capital M, this order value, we'll try to understand these things. And if w value is very large, why variance will increase? Okay, so these two things, if we can understand, then we can go for ridge regression to eliminate this overfitting. Okay, problem. So our target is to understand these things. That whenever m is increasing, w cap will explode, and it will lead to high variance. Okay. Now consider this model. So you see, this is y1 to yn. So these are your dependent variables, vectors, and this is your matrix, capital X matrix, and this is your w vector, this is your epsilon vector, error vectors, right? Now in this capital X, what is happening? As m is increasing, what is happening? So you are keeping capital N constant, data point constant, but number of data points are capital N only, but you are going to increase capital M. So in that case, the number of columns will increase, keeping number of rows same. Okay, so when this capital M will be too large compared to this capital N. Obviously, compared to number of rows, number of columns will be very large. And you see this matrix, whenever number of rows is less than, very less than compared to number of columns, you will see these column vectors are becoming linearly dependent. They cannot be linearly independent. Okay, because number of columns is more than number of rows. Okay, so as number of columns, these column vectors are not linearly independent. In that case, now if I consider x transpose x, this matrix dimension will become m cross m. So huge dimension m cross m. So you will see that in that matrix, the eigenvalues, many of the eigenvalues will become 0 or close to 0. Okay, because of this fact, because x, capital X, it is having very large number of columns compared to the number of rows. Because of this matrix, this symmetry matrix x transpose x, this is square matrix, but it is having eigenvalue almost 0. Okay, and if the eigenvalues are zeros, that is inverse. So if it is going towards 0, what is the meaning? X transpose x is becoming singular matrix, and its inverse will become almost infinite, very large. So x transpose x, its value will become very large. So this value particularly is very large, but this is not very large. Okay, but if this is multiplied with something, this value will become very large. So thus W will explode. Okay, so we can also understand these things using eigenvalue decomposition. So this one we can consider as eigenvalue decompositions, U lambda U transpose. Okay, and I said that lambda is a matrix, a diagonal matrix containing all the eigenvalues. Okay, so whenever you will consider inverse of that, so inverse will become again U and inverse of that diagonal matrix and again U transpose. And inverse of diagonal matrix will become reciprocal of eigenvalues. And reciprocal of eigenvalues means if eigenvalue is 0, 1 upon 0 will become infinite. So that component will become infinite. As a result, this inverse will become infinite almost. Okay, so meaning is that I want to highlight these things, that x transpose x is inverse is becoming very large. But this matrix elements are very large. Thus, this y cap or y hat is becoming very large. Okay. Next, so if this W vector is very large, then I'm saying that variance will be very high. Why? Now consider one example. Suppose I am having one data x1 and y1. Okay, when and independent one is x1, that time dependent is y1, and suppose it is perfectly fit, means there is no error at all. Okay, so this y1 equals to 1.5. Suppose this coefficient w0 is 1.5, w1 is 10, and w2 is 100, and it is minus 400, minus 50,000, 4,000 is 50,000, and 20% is like that. It is very large. So these coefficients are very large. So this model will fit this data point x1, y1 perfectly. That is fine. So there is no error, right? Now, if I have slight changes from x1, so x1 to x1 plus 0.1, little small value if I add it. So what you can expect? So if there is a little change in your independent variable, so obviously the dependent variable should have also little change. Not that there shouldn't be a huge change. But here you will see, if you replace this x1 by x1 plus 0.1, here, because of these high values, this value, the deviation will become very large. So earlier it was only y1, now this value will become y1 plus something very large value. Okay, so this is giving you huge variance. That is because of these large coefficients. Okay, so this is the actual problem. So whenever this m is increasing, that time W explodes, and this will lead to high variance. But we want to minimize this variance because we have to go for higher order because we don't know what is the optimal one. We have to go for that. Okay, but simultaneously we have to maintain low variance. So how to do that one? Okay, so here we can use the concept of Ridge regression, right? So Ridge regression, we can put one constraint with previous these cost functions. So we wish to minimize this y minus xw, this norm2 square, that is fine. But we'll put one condition that the norm2 of this weight vector, norm2 square weight vector, should be less than some apart value, eta, suppose. It should not go beyond certain point, certain limit. This norm2 square. So norm2 square is basically strength of this weight vector. Okay, this is your w0 square, w1 square, addition of all those terms. And if this addition is less than eta, then we are sure that no coefficient is going to be very large. No, so all the coefficients should be within certain limit. Thus, our purpose is solved. So whenever the coefficients will have some large value, then only it will lead to high variance. So you want to minimize the high variance. That's how we'll put this condition. Okay, so this is the basic formulation of Ridge regression. Okay, so this is one constant optimization problem, right? So the same problem we can consider in different way. Using Lagrange multiplier, we can include these things. We can add one penalty to norm2 square. So here this is a vector, remember, this is a vector. This norm2 square is added, multiplied with lambda, then it is added with previous cost functions, right? So this is one penalty, L2 norm, it is called L2 norm penalty. So L2 norm penalty is added with basic cost functions. We'll get one cost function, single cost function, and that we can try to minimize it. Okay. So this is single cost functions. Now we can handle these things. So this one can have one closed form solutions as earlier, but first one is very difficult to get one closed form solutions. Okay, so using Lagrange multiplier, this formulation will give you some closed form solutions, and that is very easy. Again, you can take derivative with respect to w vectors, then you can put it to null vectors, and you can solve for w cap. Okay, so if you solve that, what you will get closed form solutions. It is very similar to earlier, only this much change. You see, it will become lambda I plus x transpose x, this whole inverse, x transpose y. Okay, so this is the only change. Now you see, whenever this x transpose x is having, suppose, very low eigenvalue, close to 0, this matrix, when lambda I is added, is, so if, so its eigenvalue equal to sigma, suppose, then this one, its eigenvalue, corresponding eigenvalue, obviously lambda plus sigma. Okay, that is very simple to prove. Okay, so whenever, so earlier it was 0, now 0 plus lambda is lambda. So minimum eigenvalue will be lambda. So it cannot be 0. So if lambda is always positive quantity, remember. So this lambda is always positive. Okay. So thus this matrix lambda I plus x transpose x is always non-singular, and this inverse will exist, and it can have some finite coefficients inverse values. So its value is not going towards infinity, right? Thus we can arrest that problem that, okay, w vector is going towards infinity. No. Okay, so using these Ridge regressions, we can confine all the weight coefficients within certain limit, right? Now we'll try to understand this formulation this constant optimization problem, suppose I am considering these things W2 norm2 square is less than suppose R square. That is better. Okay, it is always positive. If I consider these things, I want to see what is the solution, exact solution using graphical methods. Now suppose I'll consider this is this green one. Okay, this is maximum distance. So this distance is capital R. This radius is R. Okay, so norm2 square. So if I consider only two-dimensional cases, so do you see this? Okay, this one is simply W0 square plus W1 square. And if I say this is equals to R square, so this is simply a equation of a circle with radius R. So this is outer circles. So this implies that our solution point should be within the circle. Okay, so if it's two-dimensional, it is a circle. This constant is becoming a circle. If it's three-dimensional, you see it's a sphere. Okay, because W0 square, W1 square plus W2 square equals to R square. It's a sphere with radius R. And if it is higher dimensional, then it is generally called L2 ball. Okay, so this constant is L2 ball. So our solution point should be within or on the surface of this L2 ball. Now suppose this one, without this constraint, this functions is having this optimal value. So this optimal value is 4. Okay, this is a location, optimal point W cap. Okay, if I don't consider, if I ignore this part, this condition, right? So you see this point is far away from this one, so it is not acceptable. We want a solution within this ball, right? So what will go? We can allow little bit more error, these ones. So first we'll consider the contours of these cost functions. So higher errors, you see. So I'll consider this thing, this contour. So contour I have written 10. 10 imply that this error is 10 everywhere on this line. Here, everywhere, this error is 10. Okay, so it is more than 4, obviously. Okay, yet you see all the points are outside this circle. So it's again not acceptable. So we should go for higher error. So it is next one is 20. Even it is away from this circle. So we need to go more. Okay, increase this errors 30, 40, 50, yet it is not coming to this point. 60, if I consider suppose 60, that time suppose if it is touching to this circle, then I can say that this is your optimal point. Okay, so this is the optimal point. You see, at that optimal point, error will become 60, though the optimal point, without considering this one, this constraint, its value is too small, only 4. We have to sacrifice these things. Okay, so 60 will be this, it will produce 60 errors. That is fine, it is acceptable. So your bias is increasing. In turn, what I'm saying that for 10 data points, the bias is more. It's 60, but it will give you less variance. That is the important thing, because weights are within the control in this range. Thus, we can minimize the variance. Okay. So we'll sacrifice a little bit in this one. Okay, this is that the bias is we're allowing to increase a little bit. So 4 to 60, but we'll control these things, the variance, right? Now, if I consider second formulation, this is norm of W minus XW, that norm square, plus lambda times norm W2 square, the single cost functions with Lagrange multiplier lambda. So if I want to minimize these things, then what will do? Okay, in graphically I want to show. Okay, so now suppose if this part is not there, then its solution is here, right? So at this point, what is the contribution of this one? Num2 square. So you can see from this origin, this is your radius, num2 square. So there I can put a circle. So that value, whatever radius value is there, r square, that r square is multiplied with lambda. That will be added with this small value. So this small value is 4. 4 plus these things, lambda times of this r square. Okay, that will be total error. So that total error, suppose here x-axis I am considering norm of w square. So when norm w square is here very large, at this point this radius square, okay, that time this total error. Okay, suppose if I consider norm2 square is 1000 and lambda is as 0.5, so 0.5 into 1000 is 500. 500 plus 4 is 504. So this value is 504. Okay, so total error is large. So you see the first component is producing very low error, but second one is huge error. The total error is huge. Okay, now if I consider little bit higher error for this one, so this is the contour 10. And that time I'll consider one circle which will touch to this one. So this point is solution point. So it will produce 10, this will produce 10, and this is the lesser radius square. Suppose it is 800, suppose norm2 square is 800. So 800 into 0.5, 400. So 400 plus 10 is 410. Okay, so at this point it is 410. So you see total error is reducing. So if you move from this to this side, initially it will reduce because this part is reducing drastically. Okay, so you see. So next 20, this will be the error reducing. Next, this will be the error reducing. Then it can happen that if I go further at 40, so this total error, so this area square times lambda plus this 40 can maybe more than this one. Okay, and again if you go further, what will happening? This value is reducing. This part is reducing, but this part is increasing rapidly. Okay, so when we will move from this to this side, the first part is increasing and second part is reducing. Okay, but total error can have this kind of shape, right? Okay, so you see this is the minimum point. So we can find the minimum because our objective is to find the minimum cost. So here we will get minimum. So this is minimum means at this point. So this is the minimum point. So this solution is also, you see, under control because the W norm2 square is finite. It's not very large. If we want to get again very small solutions, means norm of W hat should be smaller than these things, then we can increase this lambda value. The penalty we can increase, then we can reduce. So you see, so this curve, suppose I have got for lambda equal to 0.5. Similarly, if I increase this lambda equal to 2, then corresponding points may look like this. So earlier, you see, we got the minimum here. Here you can see that we can get minimum point here to our lower side. So this point, earlier this was the solution point. Now this is the solution point. So as you are increasing this lambda, because lambda is a free parameter, if you increase this lambda too high, you are giving more penalty with this L2 norm, thus weight value will be very small. The solution will be closer to the origin. Okay, so we can control these things with the help of this lambda. I hope you have got this point. Okay. Now I can show you that this ridge regression is also applicable to other fields like adaptive filtering. Suppose in least mean square algorithm, you know that the cost function is simply half into square n that I have discussed in previous lectures in the connection of these things neural network in perceptron especially. Okay, there we have considered that at a line the update rule is LMS algorithms. Okay, so the same update rule is very simple. From WK, in a recursive way, we'll get WK plus 1. So wk plus 1 equal to wk plus this correction term mu into ek into xk vectors. Okay, mu is learning coefficients. Now, if I add this constraint, the L2 norms, this penalty, okay, L2 norm penalty with this cost functions half of square n, if I modify this thing in that way, then we'll get this kind of update. So this alpha is coming here. So 1 minus alpha in wk, these things. So this update is called leaky LMS. Okay, so here alpha is within 0 to 1. So leaky LMS, basically it improves the drifting problem in LMS algorithm. The similar concept. So when the number of data is less compared to the channel length or system length, then if you use the LMS algorithm, you can see that weight value is increasing rapidly. So to keep weight values within certain limit, we can use leaky LMS. It cannot grow in towards very large value. Okay, so this is the objective. So this is especially useful for to design LMS algorithm in hardware. Okay, so anyway, this part will be discussed in detail in a adaptive filtering course. And one more thing, this overfitting problem is common in deep learning. So you'll see that in deep learning, we'll be using huge number of model parameters. Generally, it is considered more than 1 lakh. And you'll see that in that case, training samples may not be in that level. You may have few number of training samples, may not be in proportionate level. Suppose only 10,000 or 5,000 samples are available, but training parameters, model parameters are 1 lakh or more. So in that case, obviously you will get overfitting, because if you use gradient descent algorithm, it will go for overfitting. Okay, so to find the solutions, we can use that kind of regularization technique, like these things, Ridge regression. We can add penalty, from penalty. We can keep this parameter vectors with a certain control. Okay, and second solution, it could be we can increase number of data. So if model parameter is 1 lakh, and if our training samples is suppose 5 lakhs or 6 lakhs, then it is fine. It won't go for overfitting. So we need to increase the data, then it is fine. That is called data augmentation. So same data we can repeat in different form. Suppose by rotating something or by adding some little noise, we can make more data. Okay, the target value will remain same. So that is called data augmentation. And other way is dropout. So we can reduce the number of model parameters. How? So in intermediate stage, we can consider one thing, that we'll consider only very few number of parameters that we'll try to tune, and rest will keep as it is. Those will be ignored. Okay, so only very few parameters will be tuned with the samples, less number of samples, and thus number of parameters, effective parameters is less, thus it won't go for overfitting. Okay, so these are the consideration we'll be discussing in detail in deep learning, right? So this is all about the ridge regression. So in upcoming video, I'll discuss lasso regression. So actually, this ridge regression I have discussed in this lecture based on one request I received earlier. So if you have any request, if you want to get some video on certain topic, you can send me one request in the comment section. You can write it down in comment section. So if possible, I'll consider your request and I'll try to make that video first. Okay, so if you enjoy this video, you may like this one, and you may subscribe my channel if you wish to get more future videos, and please press the bell button to get immediate notification for my future videos. So thanks for watching. We'll meet in next lecture. Thank you.